Next we will discuss about the force on current carrying conductor in magnetic field. Let's see that. First we will take that one stand. So for this we will take that one. Now we will take that one aluminum rod which is will connect to that one current carrying conductor. It's about 5 centimeter. Then you can wind this and give connection to the cell. Okay, now wind it and give connection. Now current is crossing like this. Okay, aluminum rod from A to B, it is the direction of the current, and here it is, it's going up then coming down. Here what we are doing in essence, we are taking that one horseshoe magnet, then we are placing at the aluminum rod like this. Just we are placing like this. Okay, if you place this horseshoe magnet, then what will happen? Let's see that horseshoe magnet we are placing. Okay, so this is a north pole and this is south pole. Okay, so how it will experience force? Let's see that. Suppose if you take this horseshoe magnet same like this. Now what happened in the sense, this is horseshoe magnet, okay, and this one is north and this one is south. Then outside of this horseshoe magnet, how the magnetic field lines in the sense like this. Okay, so from north to south, the direction of the magnetic field lines are from north to south. Now this current carrying conductor, suppose if you take that, this is a horseshoe magnet, in this we place like this. Okay, this is the direction. So like this, the direction of the current. So we place like this. Okay, so now same thing, this current carrying conductor is now, direction of the current is now out of the board. If you place like this here, now what happens in the sense, direction of the current is out of the board. Now if you draw that magnetic field lines around this, now if using the right hand thumb rule, when direction of the current is along this thumb, then what happens? Magnetic field lines are like this. Okay, so which means like anti-clockwise direction we can say here. So this is around the current carrying conductor, but it is individually, right? So this is magnetic field lines from the horseshoe magnet, and this one is current carrying conductor around that magnetic field lines. Now this current carrying conductor we need to place into this horseshoe magnet. Then how it will experience force in a sense? Let's see that. Now generally magnetic field lines are coming from north pole to like this. You place here that current carrying conductor. Okay, current carrying conductor is placed. Now how it is magnetic field lines like this. Okay, now if it is same direction in the sense, no problem, it will come like this as usual. But here what happens in the sense, it will create some gap. Okay, so here it is uniform, no problem. Here what happens in the sense, it's created some gap so that this current carrying conductor will move towards the weak region. So this side, this direction, it will experience force. Current carrying conductor will experience force. Okay, then how we can say it's simple in the sense with using that Fleming's left hand rule. What is that? Fleming's left hand rule. Here Fleming's left hand rule, how we can say in the sense, thumb indicates that force and forefinger indicates that magnetic field direction and middle finger indicates that direction of current. Okay, so once again, thumb indicates that force or motion of the current carrying conductor, and forefinger indicates that direction of the magnetic field, and middle finger indicates that direction of the current. Okay, let's see here how it will be. Whether it is correct or not, we can check that. The direction of the current is out of the board, so that middle finger shows that out of the board, and magnetic field is downward direction, so downward direction. So thumb is showing that, which means it is matching with this direction of the force. Okay, so it is we can say. For that, to understand that simple way, we can tell that another thing. What is that in the sense? Just generally to take that magnetic field lines like this. Okay, magnetic field lines are this direction. Magnetic field lines. Direction of the current is this direction. Now, which direction it will experience force in the sense we can find out. Let's see that direction of the magnetic field is this, and direction of the current. Middle finger shows that upward, then thumb showing that into the board. Into the board. If it is your book in the sense, you can write that into the page. Into the page. So that we can say that it is into the board. We can tell. If same example, if you say that magnetic field lines are like this. Magnetic field lines are like this. Okay, the direction of the electron is given. This is the direction of the electron. Generally, direction of the electron is opposite direction to the current. Opposite direction to the current. So that if you take the direction of the current is downward direction, which means opposite to the electron. Now you can find out that which direction it will experience in the sense current is showing the downward because middle finger is direction of the current and this forefinger indicates the direction of the magnetic field and thumb is showing that out of the board. Here we can say that it is current carrying conductor, which means electron experiences force out of the board. Out of the board. If you see on your page, notebook in the sense out of the page, we can write. Okay, so like that it will experience the force. Why it is in the sense where it is creating that weak region, that direction it will move. Why? Because other side it is having that strong magnetic field region, so that it will move always towards the weak region only. Okay. So with using this left-hand Fleming rule, we can find out that direction of the force. Okay, same thing we can implement in electric motor. Electric motor in the sense, nowadays we can use grinder, mixers, motors. Okay, so many things. What not? Where is the motor? There we are using that. Okay, how it will be in the sense very very important this one. Let's draw this. One rod will be here, axle rod. For that, two split rings, which will be two split rings around this axle. Okay, with the support of these brushes. Okay, this is B1 brush and this is B2 brush. Okay, here we have given connection to the cell. Switch. Okay, now what happens? Direction of the current like this. We can say this is the armature A, B, C, D. Okay, and this is the north pole and this is south pole. What we have done in the sense, we taken that one rectangle coil which is armature, which is winded that copper wire, so many wires, and winding that we place it between these two bar magnets. Okay, so what happens in the sense, it will rotate freely between these two bar magnets. Okay, so what it will do in the sense, it will convert that electrical energy into mechanical energy. It will convert that electrical energy into mechanical energy. Let's see that how it will work. Then when the current is passing here from A to B, then B to C, C to D. So here the direction of the magnetic field is from north to south. From north to south. Direction of the magnetic field. Now using that left hand Fleming rule, we can say that direction of the magnetic field is A to B, so that A to B, and magnetic field direction is north to south. Then thumb showing that inside of the board. Inside of the board. We can say that downward direction, we can say into the board. Okay, now if you see here, which direction it will move? Let's see that. Suppose here direction of the current is downward direction, magnetic field is this, and thumb showing that out of the board, so that it is moving that upward. It is moving that upward. Suppose we can say, okay, this is armature. This is armature A, B, C, D. Okay, so now this AB part will move downward and CD part will move upward. Are you understand? So that which means it is moving in anti-clockwise direction. It is moving in anti-clockwise direction. So like this it will move. Okay, so that after completion of that half rotation, what happens in the sense? Let's see that same thing. Okay, now what happens here? This comes that A, and this is a B, and this is C, and this one is D, and A to B and C to D. Same thing. Now what happens? Direction of the magnetic field will be same only, right? Direction of the magnetic field will be same. Okay, but what happens if you check that? If you check, okay, with using left hand Fleming rule, direction of the current is downward, magnetic field is that, and thumb shows that out of the pitch. So like this, it will move that upward, and what happens here? It will move that downward. AB will move that downward, which means again clockwise direction, which means when current is moving on ABCD, okay, current is moving on ABCD, in this AB is moving downward direction and CD is moving that upward direction. Then when here what happens here, when current is moving from like this, okay, here CD is moving upward and BA is moving downward. Okay, so first part I will explain that. First, when it is ABCD, how it is happened in the sense like the anti-clockwise direction, like this it is went up. Okay, now again CD is coming to that clockwise direction, like again like this coming, which means it is not completing that rotation. Okay, it is not completing the rotation. To complete that rotation, what we have to do in essence, one device will be that will make the direction of the current is reverse. That we can call it as the split rings. We can say that split rings. What it will do in the sense, it will reverse the current. It will reverse the current. If it is reverse the current, then what happens? Let's see that. Okay, if it is reverse the current, okay. Now current is reverse. Now D to C from B to A. Okay, DCBA. Now current is going on here DCBA. Now with using that left hand Fleming rule, now what happens? Now direction of the current is C to D, and four fingers showing that magnetic field direction, thumb shows that into the board, into the page. So that we can say that this one is into the downward direction, and AB if you see direction of the current downward and magnetic field is this side, thumb showing that out of the board, so that this is out. So that again we will go that in anti-clockwise direction, so that CD will go downward direction and AB will go that upward direction. Okay, now let's see that whether it is completing that one rotation or not. We can check here. Okay, see now ABCD, A, B, C, D here. Then anti-clockwise direction, one rotation is completed. Okay, now here coming back. Again what happens? This is that CD, right? Okay, CD. Again this one is going down, so that it is completing one rotation now, one complete rotation now. How it is possible? By changing the direction of the current. Who is changed? Split rings changed. How it is changed? It is reverse the direction of the current. It is reverse the direction of the current. By reverse the direction of the current, it is completed that one complete rotation. It is acting as a, these split rings acting as a commutator. It is acting as a commutator. We can say like that. Okay, this is electric motor, very important. Okay, so just how it is working, we can say that very simple. Okay. In magnetic effects of electric current, till now we seen that from current carrying conductor, how it will produce magnetic field, from that how it will experience force, we seen that. Now we are going to that magnetic induction, which means from magnetic field, it will how it will produce that current. Then what are the phenomena? In 1820, Oersted found that the relation between current and magnetism, and 1831, Michael Faraday found that first relation, that one from magnetic field he produced that current. Then how it is possible? Let's see that first activity in this magnetic induction. He taken that one coil which is made up of that number of the turns. Okay, number of the turns. Why? In the sense it indicates that number of the turns, more turns in the sense more magnetic field. Okay, so that here he is not connecting to that any source of the current. He taken only the galvanometer. Galvanometer, why? In the sense we will use to measure that small amounts of the current. We will use to measure that small amounts of the current. Okay, so if suppose if it is finding that any current in this circuit, then it will start that deflecting. It will start that deflecting. So for this, what happened in the sense, we placing that one bar magnet here, one bar magnet. Okay, so now if it is stationary, okay, bar magnet on this coil is stationary, then there is no movement in galvanometer, which means we can say that where bar magnet is moving towards the coil, then it will start that deflecting. It will start that deflecting in a galvanometer. Okay, which means it is induced current in this coil. Inducing current in this coil, we can say. What are the phenomena are existed in the sense here? When bar magnet is moving towards the coil, there is a change of the magnetic flux. There is a change of the magnetic field, we can say. There is a change of the magnetic field. So from that, what happened? Induced EMF is produced in this current carrying conductor. Induced electromotive force. Okay, nothing but potential difference. Okay, where induced EMF is created, from that induced current is developed in this circuit. From that induced current, it is produced that magnetic field. That magnetic field is started that opposing this change of the magnetic field. So that to oppose that change of the magnetic field at this A and B points, at least it has to form that what happens, north pole it has to form. North pole in the sense the direction of the current, induced current, how it will be in the sense, suppose if you take like this, anti-clockwise direction, like this it will be. Okay, and here at the B point, if it is B point is north in the sense, at A point, what is the direction? It has to form that south. South in the sense it is clockwise direction. It will be clockwise direction, we can say. So if suppose if it is moving away from the current carrying conductor, okay, same thing if it is moving. So if you consider that another coil, I am taking that. Okay, so now what happens in the sense, it is having number of the turns. Galvanometer we have connected. Okay, now the bar magnet is moving away from the coil. Now what happens in the sense, away in the sense, there is a change of the magnetic field. What it has to do? It has to oppose that change of the magnetic field. To oppose in the sense, how it will oppose? By attracting. To attract in the sense, it has to form that south pole. With using that clock phase rule, south pole in the sense, then it has to, at this B point, it has to form that. In a, how it has to form? Clockwise it has to form. Then it will form that south, and here it will form that north. Here it is a north direction. But whereas these two coils, coil and bar magnet, is at rest in the sense, it does not produce induced current. Same thing we can say that another one, coil 1 and coil 2 we can consider. Okay, with another activity. Okay, so here what we done in the sense, we produced with using that bar magnet induced current. So we are extending this rod. Okay, then in this, what we are doing in the sense, we are taking another so many coils. of the cell and a small key. Okay, when the key is closed, current will flow in this. When current is flowing to this, we know that. Okay, when starting point, when you switch on or switch off, there is a change of the deflections in this galvanometer. There is a change of the deflection in this galvanometer, which means it is induced the current. It will be induced the current. If suppose if it is off, there is no current in this coil. Okay, in this coil 2. Okay, so what happens in the sense, in coil 1, it does not show that any reading. It does not show that any reading or any deflection. Which means, whereas it is switching on, then there is a change of deflections in this galvanometer, which means it's produced a small amount of the induced current, whereas it is switched off, again it will be deflected in opposite direction. It will deflect in opposite direction. Why it is happening in the sense, it is always opposes that change of the magnetic field. So we can say that by the magnetic field, if it produces that induced current, we can call it as the magnetic induction. We can call it as the magnetic induction. From this, we can say that a generator, we can explain this one from using this one. How in the sense, let's see, here also it will experience some force. We can explain it using that Fleming's left hand rule. Fleming's left hand rule, and thumb indicates that force and forefinger indicates that direction of the magnetic field, and middle finger indicates that direction of the induced current. Direction of the induced current. Here a lot of students will get confused. Which one we need to use that Fleming's left hand rule? Which one we need to use that Fleming's right hand rule? Where current is producing that magnetic field, for that you should use that left hand Fleming's rule, Fleming's left hand rule, and where it is producing from magnetic field induced current in the sense, there we should use that Fleming's right hand rule. Fleming's right hand rule. Okay, so let's see that how it will work on the generator. In the sense, same thing. Coil we will take and we will give connection to that one rod. Okay, so that rod, what happens in the sense, it is axis. So here we will take that one splitting nut brushes we can take. Okay, and here we will take that one bar magnet. Another one is here. Okay, this one is north and this one is south. Okay, this is the brush B1 and this is brush B2. Okay. Now what happens in the sense, from this we will give connection to that one galvanometer. Okay, why? Because it will show that reading of this induced current A, B, C, D. This is a rectangular coil we place it here. Then what happens in the sense, when it is rotated, when it is induced current is rotated, then this is the direction of this. Then this is the magnetic field. Okay, from that Fleming's right hand rule we can say that, so current is moving upward A to B and magnetic field is north to south. Then thumb showing that out of the board in the sense of upward we can say. This one will be downward, which means it goes that clockwise direction. It goes that clockwise direction. When current is moving from A, B, C, D, when current is moving from A, B, C, D, then how it will be goes in the sense, AB will move that upward direction and CD will move that downward direction. Then here what is the direction of the current in the sense, from B2 to B1 it will move. B2 to B1 it will move. If suppose after completion of that one coil, then what happens in the sense, then it will go to that DCBA. DCBA. How in the sense like this? Okay. DCBA. Okay. Now the current will go like this. Then what happens? Magnetic field lines will be like this. Okay. With using right hand Fleming's right hand rule. Here direction of the current will be D to C. Thumb will shows that upward. again what happens here, this BA will go to downward, so it will go in how it will go in clockwise direction, which means CD will move that upward and AB will go that downward, so that the direction of the current, how it will be in the sense from B1 to B2 it will go, B1 to B2, which means these generators will use that to produce a small amount of the currents in home, or according to that situation we can use it. So mainly what it will do in the sense, it will change from mechanical energy into electrical energy, mechanical energy into electrical energy, like this it will produce. In this we are having that AC generator and DC generator. AC generators will change the direction of the current, but whereas DC generator will maintain that same amount of the current it will maintain. Okay, like this, this is the quick view of this magnetic effects of electric current. Thank you.